Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This lecture is a continuation, in fact, it's part of a final series of videos for differentiation rules within a Calc 1 course. This is usually the final section within that material. You should have already mastered the derivatives of most functions, specifically polynomials, exponentials, logarithms, trigonometric functions, inverse trig functions, so on and so forth down the line. And then also the differentiation techniques, which would be like the product rule, quotient rule, chain rule, logarithmic differentiation, implicit differentiation. Those are important. Usually prior to this, you have gone through using your derivatives in applications like related rates and linear approximations and differentials. And this is sort of a round out section. It introduces a whole new style of function. And this whole new style of function is called the hyperbolic function. Now, before we go into that, I think it's very important to understand the birthplace of this style of function. And so this is an interlude. Does it mean that it's required? No, but it'll make my other videos, it will allow my other videos for you to make more sense. So let's go ahead and state Euler's formula from the get-go here. So e to the I theta, where I is the imaginary number, square root of -1. E to the I theta is equal to cosine of theta plus I times the sine of theta. This is an incredibly awesome formula within mathematics. And in fact, a lot of people will use one special angle for this to showcase the connection between E, I, 0, and 1 all in a one formula. And that is this right here. Notice I'm just subbing in pi for the angle theta. And when you do that, you get e to the I pi is equal to, well, we know the cosine of pi is -1. We know the sine of pi is 0. And so this is a very awesome equation, because if you rewrite it, you get e to the I pi plus 1 is equal to 0. And these are the 5 special constants, right? E, I, pi, 0, and 1. 0 being the additive identity, 1 being the multiplicative identity, E being that very special base, whose base of an exponential function whose derivative at 0 is 1. Also, it's the limit as x goes to infinity of 1 plus 1 over x to the x power, which is also the limit as x goes to 0 of 1 plus x raised to the 1 over x power, I being the square root of -1, and pi being the ratio of the circumference of a circle to its diameter. Now that is a really cool formula, but it's all born from this Euler's formula here, and we're going to go ahead and prove that that is true. Now, the proof relies on the fact that somebody handed us the formula. We're not deriving the formula, we're proving the formula. And I cannot be credited for this proof. This was actually done by somebody else, but a beautiful proof it is. So, and much easier. I shouldn't say much easier, but it does not require series, which is something you'd need Calc 2 for. To start this proof, we're going to actually take two different functions here. Now, to showcase that these two functions are actually the same, what I'm going to do is do, again, not what I've invented, but somebody else actually did, and I thought this was a really ingenious way of doing this, is I'm going to take the product of the reciprocal of f and g. And if that becomes a number 1, then f and g must be the same. So again, I'm going to let, so I'll say and, I'll let h of theta be the reciprocal of f times g. My hope is to show that h of theta is 1. That is, g of theta and f of theta are identical. And if that's the case, we will have proven that these two functions are equal to each other, and therefore Euler's formula is true. Now, one thing that you should note is that 1 over f is just e to the negative I theta. That's okay. And then obviously g of theta is the cosine of theta plus I sine of theta. All right. So let's go ahead and take these derivatives. Now, one thing, or I should say, now we're going to take the derivative of h here. One thing I need to mention before we continue is that all of our theorems that we've used so far within Calc 1 have been with the assumption that our coefficients or constants are real numbers. Just letting you know, a little bit of hand waving here, but all of those derivatives are still remain true if the scalar coefficients are imaginary numbers. It's just that we haven't worked over the imaginary numbers, so you haven't been able to see that, but it is true that all of our differentiation techniques still hold as long as our constants are complex numbers, so we're still fine. All right, so h prime of theta. Well, that'd be the derivative of this first function. So that's e to the e to the negative I theta. And then you have to hop inside this exponent and take the derivative of negative I theta with respect to theta. So theta is our variable, so the derivative of negative I theta is going to be a negative I. And then you multiply that by the second function, which is cosine of theta plus I sine of theta. So far, so good, I hope. Now this is the product rule, so plus. And then we have our first function, e to the I theta, negative I theta. So used to saying positive I theta, sorry about that. Times the derivative of that cosine plus I sine of theta. Derivative of the cosine is a negative sine of theta. That's not a biggie. And then plus the derivative of I sine of theta is I cosine of theta. Again, I being just a constant, a scalar constant. And now you notice both those terms in this derivative have an e to the negative I theta in common, so I'll factor those out, e negative I theta. And what I'm going to do is I'm going to take this negative I and distribute it into these parentheses here. So to do that, we get a negative I cosine of theta minus I times I, which is I squared, sine of theta. Excuse me. In the second group, we have a negative sine of theta. And we have a positive I cosine of theta. Now you can see the positive I cosine of theta and the negative I cosine of theta cancel beautifully. And you get e to the negative I theta times the quantity. I squared is a negative 1, so that's a negative 1, or in other words, a positive 1 times the sine of theta minus sine of theta. And of course, that's e to the negative I theta times 0, which is equal to 0. Now, a theorem that we have not actually been introduced to in Calc 1 as of yet, but you will be introduced to this in a future section, is that if you have a function whose derivative is 0, which we have a function here, h, whose derivative is 0, that means that function must be a constant. And that's sort of like saying that you took the derivative of a function and that derivative is 0. Well, I mean, it's not just like, it is exactly like saying that. You took the derivative of a function, the derivative is always 0. That implies that the function must have been a horizontal line, because again, the derivative is the slope of that, and the derivative everywhere is 0, so therefore it is a horizontal line, therefore the function must be constant. Let's go ahead and, do I use a C in here? No, I don't. So let's go ahead and call that constant C. So hence h of theta is equal to some constant C for some C. And just to be thorough, since we were dealing with the imaginary number system or the complex number system, I'll just say that C could be a complex number involving a non-zero imaginary part. That's not that big of a deal actually for this proof, but hence h is a constant. That is h, which is e to the negative I theta times the cosine of theta plus I sine of theta is equal to some constant C. For any value of theta you plug in, it should always be that constant, that same constant C. This equation is an identity. It will always be true. No matter what we plug in for theta, it will always, the left-hand side will always turn into the constant C. So if you plug in any theta you want, it should return the magical constant C that we're looking for. So I'm going to strategically choose a theta here that will work nicely. Specifically, I'm going to let theta equal 0. Again, you could let theta equal any angle you want. You'll get the same result, but theta equals 0 mathematically for us by hand will give a nice result. Then the following must be true. E to the 0th times cosine of 0 plus I sine of 0 must equal C. That is 1 times 1 plus 0 must equal C, or that is C must equal 1. Hence, or thus, e to the negative I theta times the cosine of theta plus I times the sine of theta is always equal to that constant of 1. Multiplying both sides by e to the positive I theta. So e to the positive I theta times e to the negative I theta times this cosine of theta plus I sine of theta. And you're multiplying both sides by e to the I theta. These, that's supposed to be an I, sorry about that. Common bases with different exponents, you would add their exponents. So I theta minus I theta, that's e to the 0th, which is 1. And so this implies cosine of theta plus I sine of theta is equal to e to the I theta. That is the end of the proof. Quod erat demonstratum. So it has been demonstrated. That is a beautiful proof, not a derivation, but a proof of Euler's formula. And it is gorgeous in its own right, but we are going to be using that same idea, Euler's formula that is, to talk about trig functions. To do so, we're going to have to recall something from the unit circle here. Well, actually, we're not going to deal with the unit circle yet, but we're going to start dealing with trig functions. So we're going to bring our trig functions, or isolate our trig functions in Euler's formula. So here's the theorem that the cosine of theta is equal to e to the I theta plus e to the negative I theta over 2, and the sine of theta is e to the I theta minus e to the negative I theta over 2i. Kind of interesting that you can write your trigonometric functions as exponentials. Very, very interesting. And this is why normally Calc 2 is required for this conversation, because you can do infinite expansions of the exponential functions here. But we already proved Euler's formula without that series expansion, and that'll make this conversation much easier without Calc 2. So proving this, by Euler's formula, e to the I theta is equal to the cosine of theta plus I sine of theta. Well, we're going to modify that slightly. We're going to let our angle be negative theta. In fact, I'm not going to say let theta equal negative theta because that's weird. I'm just going to say, and so if we allow the angle to be a negative theta, you'd have cosine of negative theta. This is just a simple substitution, plus I sine of negative theta. However, we know that cosine is an even function, so this is e to the negative I theta is equal to cosine of theta. And we know sine is an odd function. So sine of negative theta is negative sine of theta. Okay, and I'm going to call this one up here formula 1, and this is formula 2. What we're going to go ahead and do is add formula 1 to formula 2. Hence, 1 plus 2 becomes, let's see, we'll have e to the I theta on the left-hand side plus e to the negative I theta. So that's the left-hand side when you add formula, this first formula here to the second formula here. On the right-hand side, you'll have two of those cosines of thetas, and the I sines of thetas are of opposite sign, S-I-G-N sign, and so they cancel. Dividing both sides by 2, you'll get e to the I theta plus e to the negative I theta over 2 is equal to the cosine of theta. And so we have proven the formula for the cosine. It's supposed to be an I there. So that's the proof for the cosine formula. The proof for the sine formula actually is just taking 1 and subtracting 2. So I'll just write that in. Moreover, 1 minus 2 becomes, well, let's see, you take formula number 1, you'll get e to the I theta, and you're subtracting formula 2, so that'd be minus e to the negative I theta, and that's equal to cosine of theta minus cosine of theta. They cancel beautifully. I sine of theta minus a negative I sine of theta is 2i sine of theta. Now divide both sides by 2i, and that will imply that you have e to the I theta minus e to the negative I theta over 2i is equal to the sine of theta. Those two formulas, by the way, that's the end of the proof, QED. Those two formulas are super interesting because, again, it's taking our trigonometric functions, what we call our circular functions, and trading them out for exponential functions. That is, it should seem somewhat magical because exponential functions should not seem to you as being related to a circle, but they are because cosine and sine are related to a circle. So recall that if you have a point xy on the unit circle, then the x value was defined, again, on the unit circle as cosine of theta, and y was defined, again, on the unit circle as sine of theta. Let me actually draw this down below. So you have a unit circle, that is, this edge right here is 1, 0, and that point right up there is 0, 1. And if you have an arbitrary point on that circle, the x value is defined to be the cosine of theta, and the y value is defined to be the sine of theta. That was the actual original the true definition of a trigonometric function, the cosine and the sine. And in fact, it turns out that when you first define this, you define this in terms of the arc length along the circle, the length of this red kind of squiggly line there. That was originally defined to be the arc length from 1, 0 to the point x, y. And we called that theta. Technically, I think when we normally define it, it's defined as t, where the terminal side of that, it shouldn't be called the terminal side, where p is called the terminal point of that arc length theta. However, on a unit circle, we know the relationship between arc length and angles is given by the following formula: S is equal to r theta, where S is the arc length. Well, on a unit circle, r is 1, the radius, and so therefore the arc length, S, will be actually the measure of the angle in radians. So our arc length, S, is actually the same as the measure of the angle, theta. So that's why we were able to link trigonometric functions to angles. Originally, they were defined in terms of arc lengths. Little did you remember that, right? So anyhow, so now that we know that another relation exists. Specifically, if the point xy is on the unit circle at the terminal side of theta, or equivalently a distance along the arc of length theta, then the cosine of theta is defined to be, or can be turned into, I should say, e to the I theta plus e to the negative I theta over 2. So again, this cosine right here is e to the I theta plus e to the negative I theta over 2. And the sine of theta is e to the I theta minus e to the negative I theta over 2I. Very interesting little aside. Now, to further justify that this is true, remember that on a unit circle, the equation for the unit circle is x squared plus y squared is equal to 1. And that's where we get the Pythagorean identity that cosine squared plus sine squared is equal to 1. It's because cosine on the unit circle is defined to be the x value, and the sine is defined to be the y value. So you get cosine squared plus sine squared is equal to 1. But let's see if that identity, our brand new change-ups here, if those still satisfy this equation. And that will be our last example for this video. And then this will lead into our next video, which will be a conversation about hyperbolic functions. So show that these new definitions still lead to x squared plus y squared is equal to 1. Well, if x is equal to cosine of theta, which is equal to e to the I theta, I'm going to zoom in slightly here, plus e to the negative I theta over 2, and y is equal to the sine of theta, which is equal to e to the I theta minus e to the negative I theta over 2I, well then, let's go ahead and take a look at x squared. X squared must equal e to the I theta plus e to the negative I theta being squared over 4. And actually, maybe I shouldn't do the and. I'll just clean this up, which is equal to, let's see, multiplying this out, you get e to the I theta times e to the I theta, which is e to the 2I theta, plus 2 of the e to the I thetas times e to the negative I thetas, but I'm imagining that you know what's going to turn into, plus e to the negative I theta times e to the negative I theta, which is e to the negative 2I theta. And again, that's all over 4. A little bit of cleanup here. E to the I theta times e to the negative I theta is 1. And so this numerator turns into e to the 2I theta plus 2 times 1 plus e to the negative 2I theta all over 4. Now we're going to go ahead and square y. Again, we get that e to the I theta minus, in this case, e to the negative I theta. That's going to be squared. Downstairs, you get a 2i being squared, which is a 4i squared. I squared we know is a negative 1, so that's negative 4 downstairs. We'll have an e to the positive 2I theta minus 2 times e to the I theta times e to the negative I theta. And then finally, plus e to the negative 2I theta. And again, e to the I theta times e to the negative I theta. That's just a 1. So it's that middle term is going to be a -2 when everything's said and done. And what I'm going to do is factor this negative off the fraction. I dislike negatives in denominators, so I'll write this as a minus. And then we have e to the 2I theta minus 2 and then plus e to the negative 2I theta. And this is all over 4. Now remember what we're doing. We're adding x squared and y squared. So x squared plus y squared is equal to, well, when you add those up, I'm going to actually be somewhat slow about this. E to the 2I theta, this is x squared, by the way, plus 2 plus e to the negative 2I theta. That's over 4. And then remember, y squared ended up being a negative, and then we had e to the 2I theta minus 2 plus e to the negative 2I theta, all over 4. Let's see here. E to the 2I theta minus e to the 2I theta, they're gone. And e to the negative 2I theta minus an e to the negative 2I theta, those are gone as well. And so we get 2 minus a -2, which is a positive 4 over 4, which is 1. And we get that same identity. X squared plus y squared is equal to 1. So these definitions of cosine and sine, which were derived from Euler's formula, still satisfy what we need for the unit circle. So we should already know that just because we've proved that Euler's formula is true, but still it's nice to see that the justification still holds. So anyhow, this is the basis for a conversation we're going to have in the next video. And that's why I think this video is so important to watch, because we're going to then introduce the hyperbolic functions, which have something to do with these two relations right here.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.